Let's get started. Hi. So welcome to the second CFAR Methods Mini-Symposium on network modeling. I'm going to talk briefly to just introduce some basics and some terminology so people who aren't familiar with network terminology, networks, that we're all on sort of the same page, and then I'll give a brief example, a brief research example, and then we have 3 content talks, which I'll sort of prelude at the end of my talk. So I always like to start whenever I talk about networks with this very simple example. So we usually think about sexually transmitted diseases, what matters in sort of 2 dimensions, like how many partners people have and what percentage of the population is monogamous or, is having extramarital partnerships. But we can see though that this network structure matters. That doesn't tell us the whole story by looking at a little example. So here we have an average number of contacts that everybody has is 1.5. 60% of the population is monogamous. And if a disease sort of enters the population or spontaneously emerges here, it is only going to infect 4 people, about 25% of the population, and last a few generations. This population has even more monogamy and the same contact rate, but it has this guy right here who's has a lot of connections. And if the same emergence event happens, then the disease will last longer, 4 generations. I mean, it's a very small network, but will infect 60% of the population, over twice the amount of the population. So clearly, simply these very aggregate statistics about contacts and about networks are not all that matters. The network structure matters a lot. So I'm going to go through just basic terminology and network characteristics here with some discussion of why they matter. So a network, or mathematicians will call it a graph often, is just is described by nodes or vertexes and edges or links. So the nodes represent sort of units. So usually when we're talking about these, we're talking about individuals, that each node is an individual and each edge or a link is a potentially infectious contact, or a pathway under which infection can potentially flow. But it's not, you can generalize this, it's not just thinking about individuals. This could also represent communities, with the links representing flow of disease or potential flow of disease between communities, how well they're connected. So networks can be undirected, and that's generally how we think about sexual networks, right? The disease can flow one way or another. They can be directed. So for instance, a needle sharing network in any particular event is directed because it's the first person to use who can go to the second person. And then there also can be weights. So different types of contacts can have different types of ability to transmit disease. One of the most basic descriptors of networks and connectivity is the degree of the nodes. So a node's degree is just how many contacts that node has, how many edges it has going in or out of it. So in an undirected network, you have just a degree. In a directed network, you have in degree for in links and out degree for out links. So here, this node here has a degree of 4. This one has 2. And then the degree distribution describes the distribution of degree of nodes across the whole network, which has a huge influence on how the disease spreads. So a network can be described by a path, or the relationship between any two nodes can be described by a path, and we're particularly interested, which is just a link of edges and nodes linking any two nodes, and we're particularly interested in the shortest path, because that is the shortest amount of time, the shortest number of hops a disease will take to get from one individual to another individual in the network. And the span of the network is the longest, shortest path. So that's the longest time it could take a disease that somehow enters the network to get, it's the longest number of jumps it could take that disease to get to any other individual in the network. And so that's a measure of sort of how big the network is in a way. So the next idea is the idea of connected components. So this is work from one of our speakers. A connected component is some subnetwork or part of the network where every node is connected. So here, this is from an island in Malawi, right? There's this giant connected component, which we'd call the largest connected component, where all of these people on the island have some sort of link to someone else on the island. In this it's a sexual network. But then we have these smaller connected components that are independent of that, but are linked together for different parts of the island. One thing to note about this is that these are just the on-island links. There's off-island links too. So the size of these connected components is important. And then there's an idea of centrality. So centrality is a measure for the nodes, and there's a few kinds of centrality. One measure of centrality is just how many connections you have, right? But there's two other ways to think about it. One is a betweenness centrality, and that means what number of shortest paths, or what percentage of the shortest paths in a network flow through a given node. So this node has really high betweenness centrality because every other node, all the orange nodes, have to get from one to the other. You have to go through that node. All the shortest paths go through it. And that means that if you could somehow eliminate this node from the network, or make it so that transmission could not happen through this node, you couldn't get anywhere, right? So those sort of betweenness centrality nodes are very important for transmission. Another measure is closeness centrality. So this is how close is a node to all other nodes by the shortest path to those nodes. So here we have the same figure. So this node is very, very close to every other node, just as it is here. But it no longer has such high betweenness centrality because there's other paths between almost every node. So you can think of that as this is sort of a way of necessary and sufficient. If you have this, here it's sort of necessary to pass through this node. Well, here it's sort of sufficient to pass through the node to have a quick transmission. Another property of networks is a sortativity, which is a tendency of nodes or people or units to mix with similar units. And the most common example of this is age assortativity, where people of a particular age tend to mix, particularly in sexual networks, with people of about the same age. So here, this is the one-to-one line, and here we have, this red is indicating that sexual partnerships are tending to happen close to the same age, with maybe men being a little bit older. So, and this is, I did leave out one thing, which is clustering, but maybe if that's important in anybody's talks, they can bring it up. I don't know why I forgot that. So just one last sort of property I want to talk about is all the networks I've shown you are kind of been thinking about networks in this very static manner. But it's important to remember that networks that most of the networks we are concerned about for disease transmission are dynamic, right? That people, sexual partnerships aren't like just always there. They're happening at different times. And that brings this idea of concurrency in these connections, when the connections occur, because if there's no concurrency, right, like in the serial monogamy situation, then a disease, then like HIV, for instance, could only go this way on the network. Could go from 1 to 2 to 3 to 4. From one could give it to person who could give it to 2, 3, 4. But if the person got it from 5, none of these people would be at risk. Whereas if there's a lot of concurrency in the partnership, for instance, one would always be at risk from an infection occurring from all of these partnerships. So that's okay. So and just one, so that's sort of descriptors of the network, and then there's also this. We talk a lot about different network types that have different properties, and you can sort of think of a range of networks in a couple of dimensions. So one is how random the network is and how easy it is for a disease to make big jumps across the network. So at one extreme would be a regular network. So this is kind of like if we only ever had any interaction with our neighbors. So then things are very, very local. But if you take just a few of those links and rewire them to be really long jumps, it only takes a few to get what we call the small world property or a small world network. That means that everybody is very closely related to everybody else. And this is why like the sort of 6 degrees of separation theory or 6 degrees of Kevin Bacon works, because you only need a few of those big links to make everyone close. And this is slightly more random. Then in a random network, there's really no association between position and stuff and who you're linked to, so disease can flow very quickly all around. There's also this idea of how much a network follows a power law or is scale free. And that is this idea that we have hubs, very, very highly connected nodes, and they who are very, very highly connected. So we have a few of those that do a lot of dispersals for disease, and then we have sort of a lot of less connected nodes out sort of on the periphery, rather than in a sort of classic random network where everybody sort of comes from the same distribution. And this affects how quickly diseases spread, because when you hit a hub, things can go very quickly, and also you can think about if you can knock out the hub, you can have a big effect on disease transmission. The flip side of that is in these types of networks, sort of randomly distributed interventions are not very effective. So we can measure networks in a variety of ways, ranging from egocentric, where we just ask each individual, we only collect an individual's characteristics about how many contacts they have, their personal degree, and the nature of those contacts. And it ranges from sort of more complex designs, such as snowball sampling, where you're going to, sort of intelligently sample parts of the network, to a complete sociometric network, where you try to actually get information on every single person. So I'm running a little over, but I'm going to quickly go through say one thing about modeling networks and then go through an example. So there's sort of 2 approaches. Once you go out to model networks, you can and this is what we usually think of, we explicitly represent the network, we generate a network with particular characteristics, and then we actually run the disease process on the network. It's almost like an agent-based model or an individual-based model. And so that's sort of one extreme. At the other extreme, there are a lot of ways you can take sort of the classic compartmental model, the SIR model, if you've ever heard of them, and think about those and adjust them and change the ways they work to approximate the impact of different network structures through systems of differential equations. All right, so a brief example, and I'll just note that this is all courtesy of Katie Richter's work. I mean, I helped her, but she did most of this. So here we have so here we're going to talk about a study of HIV in South Africa, where there were 1,000 enumeration areas, 15 households were surveyed per enumeration area, and egocentric sexual contact data was collected. So number of partners in the last year, details on the 3 most recent partners, and for a subset, we were able to link household partners. So this is what our data looks like, is you have a degree distribution of the number of partners named by here men and women. So the distribution, so you have some people naming a ton of partners, but most people name less. And notice here that the men have a tendency to name more partners than the women. And we also have things like this age mixing matrix. This is the same one I showed you before. So we're going to take these marginal characteristics, and what Katie did is she wanted to take these marginal egocentric characteristics and actually get a distribution of what full networks looked like on this. So, she'd generate a population, create partnerships, and then optimize those partnerships to the marginal data and degree distribution, age assortativity, et cetera, that she had collected. Calculate, and then use an MCMC process to try to get a distribution of probable networks from that. One of the big assumptions, though, she ended up having to make from this to do this was how do we reconcile those being more partnerships from the men than there were women named by the women, right? You have to, there's a number disconnect there that has to be reconciled. And you can think of 2 ways to reconcile, or 3 ways to reconcile it. One is the men are lying. So we're going to just assume that the women's reports are accurate. 2 is the women are lying. So we're going to assume they have more partners than they say they have. And 3 is that there's some unseen population of highly connected women out there that are taking a lot of these male partnerships that we're not seeing. And so these bottom 2, so these are some of the network characteristics I was talking about, like so number of components, how big the largest components is, average betweenness. And the green here is from the assumption that there's this hidden population of highly connected women versus the other 2, which are the sort of uniform misreporting solutions. And you can see that you get very different network structures if you assume that there are these highly connected women out there, including having much bigger, larger components, much more betweenness, and many less components in general, meaning more people are all connected under that scenario. And that impacts, if we go and then run epidemic simulations on that, that has a huge impact on the number of infections we might see over time, right? So in the in the hidden highly connected population, that we would expect to see a much faster spreading, larger epidemic than we would in either of the uniform underreporting scenarios. So that's just a brief motivating example to give you an example. And now we're going to have 3 talks where people go into much more detail. First, Kate is going to talk about networks sort of to understand patterns of transmission at the population level. Stephane is going to talk about using networks to disseminate or spread interventions around populations. And then Jacky is going to talk about using networks structure to optimize interventions. So I ran over, but if there's any very quick question for me, I'm happy to answer it. Otherwise, we'll just give it over to Kate. All right.
Up my slides. Where is the? How do I do this?
So.
Okay, there we go. This one.
And then there is just full screen it.
Where is the?
Or just like the presentation at the end, like.
There we go.
Yeah, perfect.
Okay. Hi everyone. For those of you who don't know me, my name is Kate Grabowski, and even though it says Mary Kay, I go by my middle name, which is Kate. I'm surprised I put that up there. Anyway, so today I'm going to talk to you a little bit about the network analyses that I've been doing as part of the Rakai Community Cohort Study in the Rakai Health Sciences Program to answer a particular question. And the question is whether or not high prevalence fishing communities on Lake Victoria are seeding HIV transmission in Uganda's inland population of agrarian and trading communities. So there's a lot of spatial heterogeneity in sub-Saharan Africa. It's markedly heterogeneous. It has foci of both high HIV incidence and high prevalence communities, and also foci of low prevalence, low incidence communities. So this is a map by Sarah Anderson and Tim Hallett's group. It was published in The Lancet back in 2015, showing HIV prevalence in sub-Saharan or in Eastern Africa, and higher prevalence is in red and lower prevalence is green. So the higher prevalence areas have prevalence of upwards of 30%, and the lower prevalence areas of 0 to 5%. And you can see that within countries, there's a ton of heterogeneity. And so it's been proposed that targeting combination prevention, which I'll refer to as CHIP for short, to these high prevalence areas, or often what people refer to as hotspots, is essential for cost-efficient use of resources. And this is this whole mapping and identifying hotspots has been championed by Debbie Birx and the PEPFAR program because there are limited resources and we have to do what we can with what we have. So in Uganda, and particularly in East Africa, hotspots include Lake Victoria fishing communities, and these communities have astronomically high HIV prevalence. So their prevalence will range anywhere from 20 to 40% of adults between the ages of 15 to 49 years. So in Uganda, the national prevalence is actually between 5 to 7%. So it's substantially higher in these fishing communities compared to elsewhere in Uganda. So in 2014, the Uganda National ART guidelines recommended targeting ART to fishing communities and sort of enhanced combination prevention services, including test and treat, which is just the initiation of ART regardless of what your CD4 count is at time of diagnosis. And this test and treat strategy is really based on the assumption that fishing communities are serving as a major source of new infections among inland communities. And in fact, they actually explicitly state this in the Ministry of Health documents when they're recommending test and treat. But when we did a lit review to see whether or not there was any evidence that this was the case, there was absolutely no empirical evidence that supported this sort of source sink hypothesis with fishing communities acting as sources. So that was, and in fact, there's actually no evidence really from anywhere in sub-Saharan Africa that high prevalence areas are really seeding infection into low prevalence areas. There's not a lot of data to support that. So we wanted to actually address that question, and we submitted an R1 to do it, which was thankfully funded a few years ago. And with money from National Institutes of Allergy and Infectious Diseases and the Gates Foundation, we proposed to elucidate community network structures and to quantify the extent to which Lake Victoria fishing communities are sustaining HIV transmission. And this district, Rakai, down here in the south central Uganda, which is Rakai district. So it's this little yellow district here that's situated on Lake Victoria, bordered by Tanzania to the south, and Masaka district to the north. And so the way we proposed to look at this was by analyzing mobility or migration networks, and then looking at viral infection flows between Lake Victoria fishing communities and inland agrarian and trading communities. So the Rakai community, so to map the migration networks, we used data from the Rakai community cohort study that was collected between August 2011 and January 2015. The Rakai community cohort study, for those of you who are unfamiliar with it, is an open population-based study of adults between the ages of 15 to 49 years in 40 communities. This is a map of Rakai district and the study communities. So in blue, we have the fishing communities. We surveyed 4 of them. There's one very large one down here within the Rakai district itself. And then there's 3 smaller fishing communities up here along the coast. We have agrarian communities shown here in green, and then trading centers. They're semi-urban. There's a lot of truck traffic and markets in these places here, and then one over here in this Liantande area up here. So there's a big highway, the Trans-African National Highway, that runs up through Liantande, so there's a lot of truck traffic there. And then this is the Masaka Regional Road, which goes all the way up to Kampala, so there's also a lot of traffic and mobility because of that road network. So here is, just to give you a sense of how different the epidemic dynamics are in these different communities, I'm showing age-specific prevalence for fishing, trading, and agrarian communities in women and in men here. The fishing are in blue, the trading in yellow, and the green are the agrarian communities. And you can see that the fishing community seroprevalence is just ridiculously high. It peaks at over 60% in women 35 to 39 years, and over 40% among men between the ages of 30 to 34 years. It's just very, very high. So to map migration networks, we first had to collect data on who were migrants and not migrants in our study communities. So individuals who migrate into and out of study communities are identified during the household census that's conducted as part of the Rakai community cohort study. And we refer to individuals who migrate into communities as immigrants, and migrants who migrate out as out-migrants. And we also record information on their reason for migration, and then as a free response, their place of origin and destination. And so as part of this R01, we actually had someone painstakingly code over thousands of locations and geocode them all on maps. So when we looked at the community level data, we found that immigrants accounted for anywhere between 9 to 49% of the community population. So in this figure here, we have the out-migration rate per 100 person years on the x-axis and the immigration rate per 100 person years on the y-axis. And you can see that they're highly correlated. And in yellow, remember, these are the trading communities, and blue, the fishing communities. And you can see that these trading communities just have extremely high rates of migration. There's immense population turnover happening there every year. And so some of you who are thinking about strategizing ART care and follow-up of people, like, that's going to be a big concern. And then when we looked at how far people were moving from, they weren't actually moving that far. So the median distance from place of origin was approximately 28 kilometers with an interquartile range of 9 to 61 kilometers. Here is the cumulative distance that people were moving and trading agrarian and fishing communities. And you can see that these fishing communities were moving, people in fishing communities were moving from almost twice as far as people in agrarian and trading communities. And we actually looked at the diversity of locations. They were much more diverse in fishing communities than they were in the other communities. I guess I have this thing here. So I'm not going to spend too much time on this slide, but it is the age-specific seroprevalence of migrants, out-migrants, and local residents. And the agrarian communities in the left-hand column, the trading communities in the middle column, and the fishing communities in this right-hand column here. And in orange, we have the in-migrants, in purple, the out-migrants, and in blue, the local migrants. And these are the female fishing communities here. And you can see that the people that are moving into these fishing communities appear to have very, very high HIV prevalence already to start. So particularly in these fishing communities. So women, female migrants had substantially higher prevalence than individuals who had never moved, but we didn't see the same patterns in men. So when we actually mapped these migration networks, what we found was this, what appeared to be preferential migration of HIV positive persons into fishing communities. So in this figure here in the bottom left, we have HIV prevalence among long-term residents on the x-axis and HIV prevalence among immigrants here on the y-axis. And you can see that the prevalence among immigrants was almost as high as the prevalence among, or just as high as the prevalence among immigrants, among residents in these fishing communities. And then here are the community networks that we mapped. And in the darker red, you have higher HIV prevalence. And the thickness of the arrows represents the amount of migrants that are moving from one area to the other. So these are directed weighted networks. We talked a little bit about those before. And you can see that regardless of location, everybody who's moving into these fishing communities, they're bright red arrows. And we only are graphing edges here where the migrant population is comprising at least 1% of the total migrating population moving into those areas. So like low density connections are not mapped here. And so there's very few outward nodes out of these, coming out of these fishing areas. And that's in part because there's a ton of geographic dispersal when people are moving out of these fishing communities. So this started to beg the question whether or not these fishing communities are acting more as sinks than they are as sources. So the next thing we did was to look at the viral flow from these fishing communities to the inland communities. And this is all viral sequencing that was done as part of the Pangea HIV Consortium, which is the Bill and Melinda Gates funded consortium that's generating over 20,000 genomes in sub-Saharan Africa to do analyses like these. And we submitted over 4,000 samples as part of our CHI study, and then we reconstructed transmission networks from the genomes that were submitted to Pangea, and then used that to answer our question. And so I just want to add that Oliver Ratman has really been leading a lot of the analysis on the viral sequencing side of things. So this is the coverage in the different communities. So the 4,074 individuals we sent, we had 2,800 individuals who had sufficient sequence data to be able to do anything with it. And the coverage varied across communities. And this can be a real problem when you're doing these types of analyses. So it's always important to estimate what your sequencing coverage is. But our median coverage is 40%, and it ranged from 11 to 54%. And the fishing communities along the coast, we had a lot more data from those communities than we did from elsewhere, and that was going to be problematic, so we ultimately had to correct for that at the end of these particular analyses. So these were all next-gen sequencing data. So you'll remember that HIV-infected individuals, they get infected with one or two founder viruses, and then that virus diversifies within their body pretty quickly. And so they're infected with what we call a quasi-species of different viruses inside of them. And so here we have 3 individuals, and they have the purple or the red and the purple person, or blue person, has viral quasi-species. It's just slightly different from the different viruses. And then this green person here was infected with 2 very different viruses. And so what next-gen sequencing does is it gives us reads of approximately 250 to 350 base pair length, and it comes all jumbled up like this. And then we have to map that to an HIV genome, like this. And so you have all these little reads of varying depth across the genome. And this phyloscanner software that was developed by Chris Wyman takes these reads, maps them, and then what it does is it scans across the genome, creating these phylogenetic trees at each step across the genome. And then it compares all of these trees to one another to create networks. And I'll go a little bit more into how that's done right now. So here we have a scenario. We have this woman here this woman here in red and this man here in blue. And we want to know whether or not these 2 people are linked. And then we have a set of reference sequences from other individuals who are infected in their community. And so we map all of their reads to the genome like this. So you have the reference sequences here at the top. We have the sequences from the woman here, and we have the other sequences in blue here. And then at the end of the day, we're scanning within windows across the genome here. And this is one particular scan in this region here. It's like a 300 window here, and we get this phylogenetic tree. And so here you have all the reference sequences, the male sequences, and then the female sequences. And the female sequences appear to be nested in these male sequences. And so this particular case, we say that the male sequences are ancestral to the female sequences here. And it's this ancestry that helps us sort of determine or to maybe hypothesize that these male sequences arose before these female sequences. So the direction of transmission in this case would be from this man to this woman, although we can never rule out intermediaries between the man and the woman. And so when we see this ancestral state, we can classify the tree as such. We might also see cases where the male and the female sequences are completely intermingled, so there's no clear ancestral pattern. We might also have cases where the male sequences and the female sequences are next to each other, but they form two separate clades on the tree, and we call those situations siblings. They're not intermingled with one another, but they're not ancestral either. And then there's also the case when they're completely disconnected, and we have a bunch of reference sequences separating the male and the female. So we took all of our data from our 2,803 individuals, and we did pairwise comparisons for all individuals in the data set with reference genomes in the background. So 4.5 million pairings, and we did 335 sliding phylogenies per pair. So this is a ton of data, and this is really a lot of Ollie Ratman's work. So our data, we're supposed to get full genomes back from this, but you can see here we only have data in this region here. The data we got back was not totally complete, but this is the area where we have data. This is an example of a pairwise relationship that we're examining here. And you can see that most of the sliding windows suggested that these sequences were in fact intermingled. We had the other cases where they could have been some were ancestral between 2 to 1, and we had one in the case where it looked like the first partner was ancestral to the second. And so you can take all this data and then get a posterior probability here for which of these 4 topologies. The direction unclear represents the intermingled case here. And in this case, it looked like most of them, the direction was unclear, and most of the sequences were intermingled, as you can see up here. So we have these posterior probabilities. And so then what we can do is we make networks from these data. And the nodes here are males. The males are in blue, the females are in pink. And the edges are represented by either these ancestral relationships or intermingled. And then we're not showing edges for pairs where the posterior mode for unlinked was greater than 60%. And we can resolve those directions using a statistical algorithm. And I won't go into too much detail because we don't have a ton of time. But these were the reconstructed transmission networks we got back from all of those analyses. You can see we didn't really have any very large connected components like we saw in some of Stephane's work. But getting back to our question at hand, so now that we have these connected networks, we want to know, okay, like the people who are serving as sources of transmission in those networks, are they predominantly coming from fishing communities? So again, here's our data and where it was coming from. And then on the right, we look at all observed events with sources in fishing communities. And you can see that there were actually very few events that were coming that had sources in fishing communities and these agrarian communities. Actually, most of the transmission from fishing communities appeared to be going from another fishing community back to another fishing community. And so adjusting for differences in study participation and sequencing coverage by both age and gender within communities, we were actually able to estimate the proportion of transmissions that were coming from fishing communities to other communities, and it was about 4%. So it was very low. And most of the transmission appeared to be endogenous to fishing communities, like we were seeing in that graph. And so this figure here is the flow, the viral flow out versus the viral flow in. So fishing communities were predominantly acting as sources. You would see this median here centered greater than 1, but we actually see it's below 1, suggesting that there's more flow in than there is out. So again, suggesting that these fishing communities are acting as net sinks rather than sources. So while targeting combination prevention to these high prevalence hotspots could be highly effective in reducing HIV incidence, that will only work when the hotspots are actually the predominant source of infection. And this is not necessarily the case, as we've shown here, for the fishing communities in Lake Victoria, which appear to be acting as sinks rather than sources. And so, so we can conclude that some of these migration And phylogenetics are pretty important for guiding our targeted prevention approaches. So I hope I didn't take too long. I'm not happy to take any questions.
Time for maybe one question.
Jackie?
So Kate, I'm curious that you didn't have very many, you didn't have a large component or really any sizable components at all.
Yeah, I think that's
What is that about?
I think that's in part because the sampling fraction in these networks is so low.
So,
But there's a bunch of other analyses that we've done sort of validating these reconstruction approaches with epidemiological data. And they appear to capture the average characteristics of people who you would presume to be sources of transmission. So we do think we're getting some sort of sense of sort of transmission, like a broader sort of data set of transmission pairs within communities using these approaches. But we're definitely missing a lot of the network, for sure.
so what percentage sampling proportion do you have?
So within communities, we have a median sampling fraction of 40%, but I mean, these networks, as you saw from the migration data, are super geographically dispersed. So when we're talking about coverage, I think it's important to think like what is the coverage of the sectional network we're trying to estimate. If we look at the district, the coverage is on the order of about 10%. So I think that's a huge challenge with phylogenetic studies, particularly in African settings, or I mean, if you take like just a few samples, you're just not really going to be able to do something. This is probably the most densely sampled African site that there is, and we're still having trouble doing stuff with it. That's why we have all these other analyses to help do that. I just want to share before I stop this like last quote. This is from qualitative work we did to supplement all of this, and it did appear to suggest that there were certain high-risk marginalized groups that were really flocking to these communities and staying there. And apparently it's because there's like no policing activities along the coast, so people, if they get kicked out of the communities, just go and hang out there. So it all kind of makes sense. Okay, thanks.
That will turn it over to Stephane. Give the microphone to the next one.
I'm just gonna steal this and walk away with it.
Okay, so, well, I don't know if it's random, but we're going to talk about fishing communities again, but on a different lake further south in Africa, so in Malawi, and I'm going to talk about some studies of networks I've been involved in there. So much more old-fashioned studies where we elicit networks not by viral isolates, but by asking people about their partnerships and relationships. And so I'll talk about that. So brief introduction, not to go again over what Justin presented, but the networks we're interested in are social networks, which are made of links and individuals, or any other of those terms that we may use. And we're interested in them because HIV can spread through them if the relations they contain include sexual relations or needle sharing or more generally contacts that may spread HIV. And in that case, network epidemiology then seeks to identify and, most importantly, predict the emergence of HIV transmission pathways within networks. So try to find which are the subset of links and individuals through which HIV can spread. And so in that case, then how do we collect data about these networks and how do we find out about them? So here, I don't know if you can see this very well, but you have different ways of representing the same network through different modes of data collection. So here you have an entire simulated network of men and women over, I think, a period of 30 years. And here are the different slices, all the relations that have occurred within the first 10 years, next 10, and the last 10 years of the process. And so data collections in an actual network like this entails garnering information on both individuals and their relationships. So different from a standard epidemiological studies where you would be more interested in the individual alone. So here we also want to know about their relationships, and the different modes of data collections vary depending on how we sample each of these units on individuals and links and their links. So the main type of study, at least in the social sciences, is what we call egocentric surveys. They are based on a random sample of nodes in the population, and we ask each of these nodes to tell us about their most recent partners. We don't try to link the data, and in the end we're left with a partial picture of the network that looks like this. So all the interviewed nodes are the larger one, and the relations they report are the darker links on this figure. And then, in terms of network analysis and making network inferences, as Justin mentioned, we have to try and infer what the underlying networks look like based solely on this kind of partially observed networks, so the personal networks of the nodes. Then recently, very much growing way of collecting data on networks is what Kate presented, so I'm not going to talk about this much, but we can find out networks of transmission through techniques of molecular biology. And then finally, in public health, we do sometimes offer contact tracing and partner notification services to individuals who present at clinic. And based on this information, we can trace parts of the network until we reach the first uninfected individual, for example. Okay, so here are some of the main study designs to study network. I'm actually going to talk briefly about another type of study, which is more of a brute force type of study, in which I was involved in Malawi, is one in which we try to actually collect this entire map. So interview everybody within the population and try to gather data on each of the links that connect them. So we call that a network census, and the study I'm talking about is the Likoma network study. So it's on a small island located in the middle of Lake Malawi. So Kate was somewhere up here. We are down here, okay, in Malawi. Approximately 8,000 inhabitants live on the island. And so what we did on this island is, first of all, we conducted a household census during which we took a detailed list of all the inhabitants of the islands, including their names, where they reside, and so on and so forth, as well as recent migrants from the island, so people who have moved out of the island, and recent deaths also, okay? Also including the names and ages and various characteristics of these individuals. Then we conducted a network interview with adults on these islands to collect data on their 5 most recent partnerships, but contrary to other surveys, we try to also collect the names and identifying information on the partners with whom they engaged in sexual relationships. And finally, we try to link back these nominations through various name matching algorithms and phonetic name matching to the household census, so that we could draw then the map of the networks that connect the inhabitants of the island. And we did that between 2005 and 2013. And what we got were maps of this kind that describe the patterns of connectivity between inhabitants of the islands. So we also did HIV testing within this population through a number of home-based campaigns. So we're also able to kind of locate where the HIV-infected individuals are on these particular networks and how they are connected to each other. So those maps then allow us to kind of describe the structure of the network the way Justin was describing, identify which individuals or which group play a key role in the particular in connecting networks and in allowing HIV to transmit within those networks. And since we have it at multiple time points, we can see whether the various risk and potential HIV transmission pathways are reconfigured or displaced at some point compared to the previous round, for example. And so to give you a brief summary of those findings of that network study, well, we found that the network structures that we observed were much denser and less centralized than what were predicted by some of the models of network formation that kind of informed a lot of the modeling in HIV epidemiology. So in particular, models like the scale-free networks and models that predict a lot of connectivity through hubs. We didn't find any of this. There wasn't a set of individuals on that island that if we were to somehow remove them or isolate them from the network would interrupt transmission. Then the other thing that we found, and you may see this on this picture, are that the HIV cases are very often located on the periphery of those networks, so not in the most connected components where all those lines appear, but rather on the periphery of those networks. And we found that this was due to a number of things, including an age effect. So people may become infected at the time they are in fact in this component, and then over time they drift out of the component because they age or because their health declines, and so the long-term HIV cases tend to be tend to be located on the periphery of those networks, and also a certain degree of behavior change. So throughout the period, the incidence had been declining in lymphoma, and so declining incidence is associated very often with this type of distribution of the cases around the network rather than at its core. And finally, we found a lot of importance of short-term in-migration into the island in sustaining the local epidemic. So a lot of those cases that were on the periphery of those networks had in fact been connected to other networks through visits to the island for whatever occasion that people were going back home for example. So these were some of the main findings. But in doing this study, we also ran into a number of problems and issues we didn't expect that were related to the measurement of networks. So how do we measure the number of partnerships and their characteristics, and is that accurate? And then we also saw during the course of that study other mixing patterns emerge that we wanted to try and understand. So I'll talk briefly about those two things that are related to measurement issues. The first, it does this type of study in which we have a network census provides a unique opportunity to evaluate what respondents report about their sexual networks and relation. And so to exploit this feature, we did a series of studies of what we call he or she says and then they say, because we can compare the reports of an individual to the larger report of the networks, including the engagement of various individuals in risk behavior and things like this. And doing this type of studies, we found fairly large measurement biases and errors in measurements of concurrency and age mixing, for example. So some of those key network dynamics that we talked about earlier. So here, for example, we compared self-report about concurrency, so the number of people an individual's report being engaged in simultaneous relations with, to what other people in the network may also report about that person and their behaviors. And we compared the the prevalence of partnership concurrency under different scenarios. So the concordant scenarios, we only consider those relations that are reported by both partners in the relationship. So very reliably reported scenarios. Self-report is only what the person tells you about themselves during the survey. And the complete scenario, it includes both what the person tells you and what others tells you about her or him. Okay? And so what we found was that there were massive differences between these different scenarios in the point prevalence of concurrency, especially in some groups. So for example, up here, never married women. So we had very large differences in concurrency at that time. And also down here, married men. So there's this assumption that women underreport, men underreport. It seems a lot more complicated than this, especially because we were able to see the reporting of these relations maybe a year or 2 years down the road in follow-ups. And some of the, not some, a good chunk of the reports that weren't made by the woman here or by the married men in that case were made a year or 2 later if the relationships had lasted until then. So clear sense that this is a reporting error. But we also found that the most recent and the shortest relations almost never made it into the survey, at least among some population group, which led to very large biases in the estimates of the duration of overlap between those concurrent partnerships. So that's an important parameter in transmission model as well. And in terms of age mixing, same thing. In egocentric survey, we evaluate age mixing by asking respondents to tell us how old their partners are. So that's a big issue in places where there's limited birth registration or knowledge of age in particular. And in Licoma, we could compare what the age of the partner as reported by the respondent to the age that the partners report himself or herself. And we found pretty good specificity, so a lot of those relations that were close in age. So here it's about the classification of relations as more than 5 years older than the respondent or less than 5 years older than the respondent. So respondents were pretty good at identifying relations with respondents close in age, but relations with respondents older in age had very, very poor sensitivity. So only a quarter of those relations reported as being in fact distant in age. So that seems to be a problem, especially because this type of input data then are used to model those networks and to project those networks from egocentric data. So it's a problem we run into. So how do we address those? Well, in several ways. Improved methodologies for egocentric network data collection, that's one, maybe ECASI or other more confidential modes. Developing imputation or correction factors in statistical models of network formation. I think that's a very active area of research. And also sensitivity analysis in network analysis, trying to find out how robust our results and network inferences are for measurement errors. How much time do I have left? Not much? 2 minutes?
Yeah, 2 minutes. Thank you.
Okay, I'll take that. And then final thing that I'll talk about is some of the dynamics of networks we observed during a time that coincided in Malawi with very rapid expansion of HIV programs. So, for example, as part of the study, we conducted 2 home-based HIV testing campaigns. The Ministry of Health conducted a bunch of other community-based HIV testing events, HIV testing week, things like this. And more importantly, ARV treatment became available at the local hospital. So what we wanted to find out is whether the availability of services, such services for prevention and treatment, modify network formation in some ways, and whether the network dynamics that emerge may modify the effects of these prevention activities. So very often that's couched under the terms of risk compensation, just sort of trying to find out whether people use condoms less often or whether they have more partners because they think the risk is lower. So we wanted to look more in terms of partner choice and whether that changes the way people select their partners when such options become available. And in particular, we wanted to find out how art patients chose their partners and if they displayed some sort of assortativity or homophily based on treatment status. So if they choose their preferentially partners who are also on treatment rather than partners chosen at random in the population. And we did find some clusters of art patients within our networks, and we try to find out whether they may have an impact on the population level effect of ARV treatment in reducing HIV incidence. And we think so because of that particular mechanism. So here you have a set of people. The blue triangle are on treatment, are on art treatment, and the red triangle is an untreated HIV positive person. The circles are uninfected, and so in this network they're disseminated throughout the component here. Whereas in this particular network, displaying homophily based on treatment, our hypothetical patients are on one side in their cluster, okay? And so what that does in that particular context is that it increases the risk of exposure to the risk of transmission among the HIV negatives by putting them into contact with somebody who's likely more infective, okay? And so we modeled that and put that into a simple mathematical model of the effects of art clusters on the population level effects of art. And we found that if these clusters emerge, they may modify the effects of treatment on HIV incidence, depending on a bunch of other things, prevalence, treatment coverage, and adherence as well. And in places with low prevalence, the emergence of art clusters, so art patients mixing with each other, can help offset, for example, poor adherence to treatment, because those who remain infective are in a separate clusters and they cannot expose others to the risk of HIV infection. But in high prevalence contexts, on the other hand, those art clusters may reduce the expected effects of art, especially if there's very good adherence, because in those contexts, you want those individuals who are less infective to get in the middle of sexual networks so they can break chains of transmission. And that's an effect that you would not get if they mix among each other. Okay? So in conclusion, briefly about the network dynamics that emerged during the course of prevention and treatment scale-up. First, they're hard to measure, and that's something to keep in mind. Measurement errors, incomplete sampling, and missing data. They may be much more complex than we currently consider in network and epidemic models, trial planning, and so on and so forth. And they may have large effects on effectiveness of interventions and the number of infections we're able to avert. Okay, and I'll keep it there. Thank you.
Maybe time for one question again while we wait for Jacky to get set up.
Oh.
So, yeah, I'll ask a question. So, how is there any context, like, is this so unique you're not able to test the generalizability of some of these findings, or have you tried to see if some of these results and sort of who people name and stuff extend to other settings?
Yeah, so that's the question that always comes back, and I don't have a good answer, except that the NIH repeatedly refused to fund studies elsewhere to verify that. But in terms of other network maps of I think there are some in other contexts, US high schools, Chinese villages, that type of stuff. But for sub-Saharan countries, I'm not entirely sure. I think there's one being planned in South Africa at the Africa Center.
Right. And you're fairly unique too, because you've done it multiple times.
Yeah,
Right? So
yeah.
you have the dynamics.
Yes, so at least parts of them during the early ramp-up of treatment.
Sorry.
No.
Another question. Have you asked people why they didn't report partnerships?
No, that we haven't done because, because we do all the linkages ex post, so we don't know on the spot who reported or not.
We have a study ongoing right now that's trying to figure out.
So thank you. Thank you for having me. So I'm Jacky Jennings. I'm an associate professor in pediatrics in the School of Medicine, but I like to say I was born and raised in Epi here. And I will be talking about HIV networks in space. I often talk about space and venues interchangeably, so if I use those, just understand that they're the same. And I'll be talking about opportunities for optimizing interventions for priority populations. I don't have a lovely French accent, and I'm not going to show phylogenetics, that's not my work. But hopefully this will illustrate some of the work that's going on here in Baltimore City, where you may be very familiar with the fact that we have quite an epidemic of HIV and now also a syndemic of syphilis going on, particularly among men who report having sex with other men here in Baltimore City. I'm not going to spend a lot of time on the local epidemic because I think many of you are familiar, although I'll give you a few statistics. In 2015, there were approximately 18,000 people living with HIV. And in that same year, there were 557 new diagnoses of HIV here in Baltimore City. 75% of those were male, and among those, 47% reported sex with a male. So that is the population that really is, we consider a priority population here in Baltimore City, and we're doing a lot of work with the Baltimore City. I should also mention that this work is in close collaboration with the Baltimore City. We've been working with them for about 18 years, providing technical capacity and really looking to augment routine surveillance information to allow us to, in an ongoing way, monitor and optimize practice-based interventions. So HIV control. Prevention tools are most effective if they are implemented at the right time, in the right space or the right place, and with the most important populations, so priority populations. And control strategies often focus on individuals, although that's not going to be the focus of my talk, and I'll explain why, and on those individuals that are most likely to transmit. So we may all be familiar with the age-old use of contact tracing, where an infected individual, we then find out about the sex partners of those individuals, and we look to notify that individual that they're infected, but also their sex partners that they may have been exposed. And it's a classic age-old technique. We also often focus on those most at risk for acquisition, and with great fortune, we now have HIV pre-exposure prophylaxis. So we have a tool, a very highly effective tool, or efficacious tool, 96%, to deliver to reduce acquisition. Critical to this strategy, I'll argue, at the population level, so individual level interventions are sometimes challenging, but if we move to a more population level focus, critical is identifying factors or spaces that precipitate the mixing of uninfecteds and infected people, or susceptibles, infecteds and susceptibles, and prioritizing sexual networks associated with ongoing transmission. So when I talk about ongoing transmission, I think about a number of things. And whenever I move to the population level, I think very quickly about the STI reproductive rate equation and thinking about necessary and sufficient causes for ongoing transmission in a population. So I think a lot about, with transmission networks, a lot about the composition of those transmission networks, that they include infected individuals most likely to transmit. So we may measure that as the viral load of the individuals, or there's a lovely paper that recently came out by John Schneider that talks about the viral load of networks. We're going to be talking about the viral load of venues or spaces. And we often talk about an infectious viral load of greater than 1,500 copies per ml, which was based on the early Quinn study in Rakai that showed no transmission events below that level among serodiscordant couples. Then, of course, we need susceptibles in that network for there to be transmission events and behaviors associated with transmission. So, for example, non-condom use, but we can think about concurrency, as Stephane talked very clearly about. And then, so disease is necessary. So we can sort of put that whole piece, disease is necessary and susceptibles are necessary. But what's also necessary for HIV that has actually a low transmission efficiency for sexual contact is density or highly connected, interconnected network structures. And leveraging these two considerations may yield more cost-effective methods to reduce the spread of HIV and thus reduce epidemic and endemic rates in communities. So now we're going to move to, so as we're thinking about population level, we're going to move to the idea of social spaces as being important points of access to identify but also access ongoing transmission networks. And so these are spaces where individuals congregate to socialize. We can think of many that we frequent, many that we frequent, and those can include online venues. That may be Facebook, Gram, as my kids say. You know, don't say Instagram, Mom. We're gramming these days. Or other apps, Grindr, Jacked, and there are many others, Daddy Hunt, many other that are Match.com. There are many other sites that we go on and socialize with other people. And then there are physical venues or spaces. You may go to a bar or a club. You may go to a park. You may go to a street corner. And these are places that we regularly frequent and meet our friends or meet our sex partners. And these places create opportunities for networks to form, right? So again, or be maintained or reinforced. And features of the spaces may increase network density. So if you can think about Facebook, for example, on Facebook, you can see, or friends are often suggested to you, right? And those friends are sometimes friends of your friends, right? Or you have some connection with, and those are suggested. So that's one method. And if you click and say yes, 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 you're increasing the density of your network, if you will, your friend network. But what may also be important is the connectivity between spaces. So when individuals, and this is really going to be the focus of this work that I'm going to show today, is when individuals frequent more than one space, and other individuals frequent more than one space, and then those spaces, if you will, become connected in a network. We often have thought about, in the past we thought about neighborhoods as islands, not being connected to one another, even though that it sort of sounds ridiculous, right, on face value, but we did analyses very much with neighborhoods not being thought of as independent. Well, we also similarly often think about these social spaces as independent spaces, when in fact, in reality, we move between them, and there is connectivity between them. So these social spaces may present opportunities for prevention and control activities by themselves, but also we could think about optimizing the interventions due to the connectivity or harnessing the connectivity of the venues. So what I'm talking about in simplistic form, so you already have seen that this is the index, and these are sex partners. So I may ask an individual, let's say, who is infected with syphilis, who are your most recent sex partners? So who did you have sex with in the past 3 months? And that's a classic contact tracing. What we started about 18, I always get these numbers wrong, about maybe 15 years ago, as a part of what was called a syphilis elimination program in collaboration with the Baltimore City. As a part of these interviews, which are called partner services interviews, routine data collection, surveillance data collection, we added local use variables where we asked, where did you meet your sex partner in the past 3 months? So now we have a host of spaces that people report meeting their sex partners. We've done other work to look at what are those spaces or venues, how have they changed over time, how have we seen the emergence of internet venues, And we've published some work on that. And with the interest of saying, are there some stable places that we could continue to go and do prevention activities? Are there others that are really emergent and are changing all the time, and how would we address those? So what we're going to move to is called a sexual affiliation network analysis. This is where individuals are connected that nominate sex partner meeting venues or spaces into a sexual network of spaces. It's an indirect source of data on sexual networks, which doesn't require contact tracing of the individuals. So if you could imagine, if you ask me about my sex partners, I might not tell you all of my sex partners. And I might give you a biased set of sex partners. I may not know some of the sex partner names. I may not be willing to divulge. And so we have seen lots of biases based on trying to connect those sexual networks. So instead, this may represent, it doesn't require that tracing of the direct contact. It may reveal places where important sexual connections may be forming, and these are potential access points. And then also important clusters of sexual connections are occurring. It's less resource intensive to obtain, I would argue, and as I mentioned, fewer biases. So what are the gaps? So the analyses that I'm going to show, we're looking to address some of the current gaps in sexual affiliation network analyses. One question has been, there have been lots of maps, you've seen them, of sexual networks, and fewer, but some maps of these social places. But really very few studies have looked to measure some of the network properties of these spaces. And to say, do they really add value? So if we take some of the measures that Justin mentioned early, betweenness, degree centrality, are they meaningful? Do they help us if we're thinking about optimizing interventions? And then we were also looking to fill the gap of measuring and quantifying transmission variability of spaces. So in this case, I'll show you how we used viral load of individuals and attribute it to spaces and look to see whether there was variability in viral loads or social space viral loads. And then the question remains how to harness this information for prevention and control. So the objectives specifically were to determine the extent to which newly HIV diagnosed MSM, so again, this is our priority population, are linked through sex partner meeting space affiliation networks, to identify the structure in, for example, density centrality of the venue network, to describe variability of viral load across the venue network or space network. And the overall goal was to inform local space-based strategies for public health HIV control to effectively reduce HIV transmission among a priority population. So the methods, again, as I mentioned, we were using HIV public health surveillance data, in this case for a subset of data from October 2012 to June 2014. And this is when we started the implementation of a new, what we call a surveillance viral load protocol, whereby we started testing all individuals diagnosed with HIV through the Baltimore Disease Control Laboratory for viral load. So separate and distinct from an in-care viral load. We also obtain those in-care viral loads, which are mandatory reported to the state of Maryland, and we combine those together to get a robust set of viral load information. The study population included 256 newly diagnosed MSM, 85% had, or 214 had a partner services interview, and 66% or 143 named at least one sex partner meeting space in the past 12 months, yielding 315 meeting place reports. Cases with versus without sex partner meeting information were slightly younger and reported slightly more sex partners. Racial distributions and mean viral load were not significantly different between those cases with and without sex partner meeting information. For these analyses, descriptive and network analyses, we perform them using the social network package, analytic package in R. And I should mention this work was done by a great team and really led by a doctoral student who was here in the epi department, Meredith Riley Brantley, Brantley's her last name. And she just did a fabulous job on the analytics. So I wanted to mention. So this shows characteristics of newly diagnosed HIV-infected MSM reporting greater than or equal to one sex partner meeting place. And on average, they were 25 years of age, 86% were Black or African American, 71% reported greater than or equal to 2 sex partners in the past 12 months. And 29% had a viral load that we classified as high. In this case, the classification, this is going to change for venues, but in this case, the classification is greater than 1,500 copies per ml. Sex partner meeting spaces. So this tells you a little bit about those places that they nominated, they told us about. Again, there were 315, there were 132 unique. I'm going to show you the distributions on the 315, but they really mirror the 132. So these proportions would be similar. So it may not be a surprise to you, but 48% were internet-based sites. 23% were bars and clubs, and these were really the predominant across the reported places. But we also had mentioned 13% were streets, parks, or neighborhoods. So I should mention, because this always comes up as a question, we had specific places reported. We then typologized these places. So we looked them up, we geocoded them to find out what types of places they were. Were they a bar? Were they a club? We were able to identify 99% of them, which was pretty amazing, except for those where they said, where it was totally unidentifiable, like a private residence. Or so then there were other venues, and then markets and malls was another typology, and private residences. So this shows the affiliation network of newly diagnosed MSM and their sex partner meeting spaces. So to orient you a little bit, the circles are individuals. So we're used to seeing this as all sex partners, right? Egos and their sex partners. But this actually, these represent venues. And if you can see the name, so of course this one features prominently, and this is Web 11. And what you can see here is a very large component in the middle here. And then along the periphery, these dyads or triads where two individuals reported, this is a park or a neighborhood, 32. This is just reported by one person. And you start to see how the venues or the spaces start to be connected to one another. And you also start to see those that are more highly reported. Are there any questions about this?
So I have a question. So
Yeah.
like one of these would be like Grindr or
Exactly.
Facebook or
Exactly.
whatever it might
Yeah.
be.
Those that are web, maybe those, right? And then there are bars and clubs interspersed here. What you also might not be able to see from your perspective is that the large component and central in this large component mostly are the web sites or internet sites and the bars and clubs. So then what we did next was take just those sex partner meeting spaces reported by more than one MSM. So this is an affiliation network of newly diagnosed MSM representing 113 or 79% of the total. These included 26 sex partner meeting places or 20% of the total. So you already start seeing that we're getting quite centralized or focused on just a many fewer venues or spaces. And again, these are the individuals and these are the venues. Now what we do is a one-mode connectivity network. And this is a co-occurrence network of sex partner meeting spaces. So we basically take away the people, and we now start to illuminate the connections that are created between the spaces or the venues. And here's where we started to measure some network properties. So the first one that we measured was degree centrality, and this is defined as the connection to the highest number of other venues. And here, Web 11 was connected to the most, or to the highest number of other venues. And overall, there was a very high degree of connectedness across the entire network, with an average of each venue venues were on average connected to 5.5 other venues. So Web 11 featured as the top, with the top measure of degree centrality, followed by bar 5, followed by Web 15. And the scale of the size of the venue or space is representative of the degree centrality. Next, we measured tie strength or betweenness. And this is defined as more shared cases between venues. And in this case, bar 5 popped up as having the greatest tie strength, and this is represented by the what did you call it earlier? The density of the lines, if you will.
Right.
There's another way to say
Weight.
that, but the weight of the lines. Thank you. So the weight of the lines. So we still held the scale of the venues, but now what you see also, you can illustrated by the weight of the lines, is the tie strength between. And what we saw here was that bar 5 featured prominently, followed by web 11, followed by web 1. And some of the lines are not showing up very well here. It's just because of the contrast. What also showed up was that there was actually a very tight cluster when we looked at betweenness of web 11 with web 13, bar 5, bar 15, and web 1. So 5 venues were clustered in terms of this betweenness measure. This is another way to look at the data. So what you see illustrated here is venue case degree, or the number of reports ranked. It's ranked by venue case degree, and what I'll talk about in a minute is we also overlaid now the space viral loads, and I'll talk about how we calculated that. So very quickly, what you can see is that 66%, 6 venues, web 11, 1, 15, and these names should start becoming familiar, bar 5, 13, and bar 10, so 4 webs and 2 bar clubs, represented 66% of all the reports about sex partner meeting places. So a highly clustered group of 6 were reported. And now what you see overlaid is viral load information. So we took individual viral loads, we attributed them to the venue and created a geometric mean for the venue or space. And we classified them by high viral load, moderate, and low viral load. 4 venues could be classified as high viral load, or 17%, and 19 or 78% were moderate viral loads. There were 3 that we couldn't calculate a viral load for. And in this case we changed our classification slightly, where high viral load is our venues that have greater than 50,000 copies per ml, and moderate viral load are those that are greater than 1,500 copies per ml. So what you also see is that all of the top 6 were moderate viral loads, but certainly above a transmission threshold of 1,500. And these are the 4 classified as high viral loads. I think that's all I want to say about that. So now moving back to our network connectivity, we were very curious to say how connected are these high viral loads to the other clusters. And the most central venue was a moderate transmission risk, but it was highly connected to web 74, and also connected, although you can't see the connections here, to bar 8, which represent the high transmission viral loads. So affiliation network analyses revealed that the majority of MSM, 79%, were linked to a network of only 26 sex partner meeting places. There was a very high degree of network connectedness across the space, suggesting that a large proportion of cases met sex partners at multiple venues. There were a specific cluster of 6 spaces representing 66% of all reports, which is quite amazing. And they were only bars and clubs and internet-based sites, and they were characterized by both moderate and high space viral loads. And the high space viral loads overall, and so overall there was a very high space viral load, and it was the highest were connected to the highly connected cluster. This suggests that there's the necessary and sufficient factors in the venue network for ongoing transmission, high connectivity. And the pattern suggests there may be very, very good opportunities to utilize new tools such as PrEP and other prevention strategies at these spaces or venues, particularly those with the highest venue case degree centrality and bridge venues. So we're very much thinking about which are those bridge venues. We could just say, okay, let's go for the 6, but we're also concerned that there may be other venues that we would miss. There's lots of ongoing work in this area through a project called Impact. There's ongoing work to examine how these networks may change over time. We're also doing now work with the syphilis epidemic that's been going on to better understand the transmission networks whether they're really overlapping transmission networks with syphilis and HIV. We're doing some phylogenetic analyses actually that Kate is partnering with, and Errol Fields is leading as a part of a CFAR Scholar Award to look at how the phylogenetic transmission structures relate to these venue-based structures. And we're already starting to test how to access, because right now the Public Health Department does not have a strategy at all for online venues. So Errol is leading some work as a part of a MARI award to start to figure out how best to access and working with owners and managers of these online venues to access populations that are at risk. So this is just the beginning of the work with syphilis and HIV. The red dots are syphilis venues. The blue dots, syphilis infected individuals. The blue dots are HIV infected individuals. And the black dots are those that are co-infected, and the squares are the venues. So I'll leave you with that diagram. Thank you.
So technically, we're at the end of our time, but I'm sure Jacky would be willing to take a couple questions if there are any.
You don't want to know what those venues were?
I do.
Totally, right? So I don't list that because, of course, we think about it like an outbreak investigation. You have to be careful about divulging somebody's livelihood, if you will. But so we're thinking about how to manage the actual names. But yes, we have all the names. We know exactly what the top 10 are, and I think you could imagine some of them already.
Are the top ones for your syphilis the top ones that were for the young?
So
I see there's like 3 or 4 that jump out there.
The top 10 for HIV and the top 10 for syphilis, 9 overlap directly, and the other 2 are in the top 12. So they're basically the same. But it is interesting to sort of, when you look at this just with the venues, there are some separate, you can't really see it that well yet, but there are some little clusters of syphilis. The question would be too, is HIV going to move in there next, right? Is it just a function of time? Which some of our analyses would argue, yes, it's just a function of time.
And do you have more syphilis than HIV?
No.
Okay.
No, but we have been having an epidemic.
It would be interesting to see how those maps change over time, or the graphs change over time with a lot of the online meeting apps. Now, people can show whether they're on PrEP or off PrEP
Yes.
As an indicator. So I'd be curious to see if syphilis remains at the levels and HIV changes in terms of those things.
And some of those changes to apps have actually been led by Dan Wolfhaler, who's leading a Healthy Online Communities project out of San Francisco. He also works for the CDC. So really having some structural change objectives in, what information you can share, right? Because there has been a lot of variability in the past, but now there's much more ability to say all different types of status, which is very exciting. But yes, we're looking at that at this moment, what they look like over time, also in the context of a syphilis epidemic, what it looks like over time. So we look forward to that.
All right, let's
Kavan?
maybe thank our speaker. Well,
One more from Kavan.
One more
Yeah.
question, but really keep it fast.
Yeah, I was just curious. Does time to sex for the online venues, does time from connection to sex, sexual encounter, does it differ from those online venues from like something that's specifically for dating versus something that's like more like Instagram or Facebook?
That's a great question. I have no idea because we don't know a lot about that journey or the time or how people are using them. There are anecdotal reports, a lot of these geospatial networking apps where people are using them in physical bars and clubs to then access people in that space. But we also see that people are using them and reporting meeting other people other places. So I think those are all great questions that we don't know yet. Yeah. And we're using a very rough tool, which is surveillance data. Thank you.
Thank you.